function. And Angela will not be able to be with us again today. So
Okay.
we will we'll go ahead and get started. I brought up can everyone see the screen that I have of week 3?
Yep.
Okay, so let's just quickly look at what we are looking at this week. We're going to be, once again, you're going to see all sorts of learning objectives here that we've covered in some ways. The important thing is this last one, learning objective 0501. Which is to describe the parts of a graph, etc. We're going to start with that. And then we will move on to looking at different types of graphs and their use in terms of business and in terms of algebra. We can use them actually to solve algebraic equations. And it's a way that will help us see other ways of doing things. But we're going to talk about different graphs. Then we're looking at your assignment this week. Will be to look here at these. These look complicated, but they're really not. What I would remind you is that many of these things can be solved using Excel financial function equations. And what you need to do is understand the terms so that you can put in the right data. But Excel can do these complicated things, 1 plus r over n to the n minus 1. And R is the rate, N is the number of payments. Okay?
Oh, that's simple.
Yeah, pretty much.
So it's a lot simpler than it looks.
Yeah.
You're just like, what the heck is that?
Right, exactly. So it gets a little more complicated when you have continuous interest accumulation, but that's just, again, a formula. And all of these others are the same thing. We've got simple interest. That is the earned amount of simple interest on either the amount you earn by loaning money or the amount you earn by depositing it. So the interest is the principal times the rate times the amount of time. And then there's compound interest. And you'll note that in the compound interest formula, there is a multiplied factor, NT, okay? So that's the number of payments and the time, okay? So compound interest includes interest on the interest. Financial people considered compound interest to be either the most brilliant thing ever invented or a tool of the devil.
Sorry.
Yeah.
I'm kind of in the in-between there because like I really wanted to learn it, but it's looking like it's gibberish, you know?
Well, Harley, do you remember in John's class when we were doing the formulas in Excel?
Yeah.
That's both of those that he just went over are the ones that John was going over in Excel. It's just different.
Yeah.
Instead of just being in that line.
Right.
Yeah.
So we'll kind of refresh our brains on it then today.
Yes.
Okay, awesome. That's good.
We will be looking at these kinds of equations as part of your assignment for the week. We'll cover some of this material in more depth probably on Wednesday.
Okay.
We might get to it today. I won't promise that because, first off, it's hard for me to talk for 3¼ hours. It's hard for you to listen for 3¼ hours, and it's one of the downsides. we'll go through a lot of material anyway, and we'll talk about different kinds of equations. These equations look a lot more complicated than they are. Once you understand how to structure them, then it's just PEMDAS. And of course, doing it in Excel, you're not thinking about that. But the fact of the matter is, once you understand, math looks mysterious because of all of the different letters and things that we put into it and structures. But if you understand what each of these terms is supposed to mean, in this compound interest, this is the amount of compound interest earned. This is the principal times 1 plus the rate divided by the number. The rate is the annual rate, and the number N is the number of payments in that rate. Okay, so if you have a 6% loan, that accrues compounds monthly, you have 0.06 divided by 12. Okay. If it's compounded continuously, it's a little more difficult. That's actually a calculus problem, which Excel solves very well. But we won't go into that. We will assume that there is that it's compounded on a fixed schedule. Many loans will compound daily. So then you have R over 365. Okay. And then this is the number of payments, pardon?
365 days of the year.
Yep, 365 days of the year.
Gotcha.
So the R here is the annual rate. Okay, the stated annual rate. N is the number of payments, T is the amount of time. So if you're in a different field, say home construction or whatever, areas of a circle, areas of a triangle, and so forth. Again, knowing what these symbols mean, pi being a constant, 3.14159, blah, 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 forever, times the square of the radius of the circle. The radius is the distance from the center point of a circle to the circumference, the outside. So knowing what these are, you just put the numbers in and solve the equation. Okay. So we have, we have a distance here, and if you're calculating how long it's how long it's going to take you to get somewhere, you'd use this formula, perhaps rearranged to solve for t. But this is the distance to be traveled, the speed, the rate. Again, don't confuse this with the interest rate. Rate in this case means how fast you're going. And it assumes that your rate stays constant. And then the amount of time will give you the distance. So if you're driving down to, say, Albuquerque, you know the distance, you know your average speed on I-25, and of course, you may discover that your average speed is, it's going to be a composite of going through the cities and then being on the open highway at 75 miles an hour, but you know that your average speed will be, say, 65 miles an hour, so you can calculate how long it'll take you to drive to Albuquerque. Okay. The volume of a box, a rectangular solid, is the height times the width times the depth. This sometimes will be abbreviated L for length. Okay, length, width, and depth. So there is one of the things that we have for these kinds of things. So it's easy enough to do if you know what the abbreviations stand for. Excel actually tells you. So if you can't remember, you pull up the formula and Excel will tell you what each of the variables is and allow you to go from there. Go ahead.
Sorry, how do you pull up a formula in Excel?
Okay.
Do they have a button formulas?
Yeah, there is a along the top line, the usual Microsoft line, you'll see formulas. And you just call that up and they will give you a list, and then they'll give you some others. If you don't see, when you take statistics, if you haven't already, when you're using Excel, which I always encourage my students in statistics to do, you'll find that you have to call down the list of others, and that's where the statistical formulas lie. So there are a lot of formulas. There's financial formulas. There's many formulas in Excel. They have a real good selection. I will warn you, especially when you get into statistics, some of them don't work very well because of the structure of their formulas, but most of them will return exactly the answers you need.
Oh,
Okay, does that make sense, Harley? Have you been taking a look at Excel?
I was.
Okay.
My computer's wanting to wig out though, so I better stop that.
Okay.
I got too
Um,
many things pulled up.
So these references that are in this assignment, I suggest you take a look at ones that cover things that we haven't covered very well. I don't think any of you need to look up PEMDAS. You all seem to know that pretty well. But when you're on a new topic, some of these will be useful to you. Let's see.
And we have a worksheet that it's attached to the assignment?
Yes. You have a worksheet that you'll be submitting.
Okay.
This is, okay?
All righty.
All right. So let's back up.
And that's in Word too, right?
That one is, yes.
Okay.
Okay, this week's discussion starts off talking about graphs. So I'm going to just quickly start on that and then pull up another document that I put together. Graphs are used for many purposes. Most of you are going into business and that are in this class. And so you will see all kinds of graphs. Some of them are pretty straightforward. Others need a little study. But there are all sorts of things that you need to think about when looking at why we use graphs in business. One is that we often have very, very large amounts of data. If you're looking at doing, especially if you're asked to do a trend analysis on sales by month over the last 10 years, which I've actually seen done. So you've got 120 points of data. Putting that much data into a table and handing it to somebody and saying, here's what it means, their eyes will simply roll into the back of their head and they will leave the room mentally, if not physically, because all those numbers are confusing. Even a lot of corporate executives will look at a table of numbers and throw it back at you and said, what does this mean? Graphical analysis and presentation is one of the best ways to do that because you have this visual gestalt of all the data, all of this stuff in one simple, apparently simple um, um, illustration that can actually show quite thoroughly what it is that you're presenting. And we'll talk about those presentations in the next little while. But every axis has, every graph has an origin, a 0 point. Many of your business graphs will just use this quadrant right here. We call this a quadrant because there are 4 of them. Anytime you take 2 lines and bisect them or link them together, you have set out 4 different areas on that page. Each one is a quadrant. By convention, we go to the quadrant in the upper right, and we call that quadrant 1. And then we go counterclockwise to quadrant 2, 3, and 4.
Can you spell that? Oh, never mind. I think I got it. Is it R-A-N-T?
Yes,
Okay.
yes.
Thank you. My
Okay,
eyes aren't that good.
So that's how we arrange them. The 0 point is called the origin. This is where, if we're looking at these, again, by convention, we call the horizontal line the x-axis and the vertical line the y-axis. We could call them the a-axis and b-axis. But in general, when this notation was developed by René Descartes, he called it x and y. So we've stayed there. The origin is the point where x and y are equal to 0. And then positive numbers go to the right of the y-axis. Negative numbers on the x-axis go to the left. And the positive numbers on the y-axis go up, the negative numbers go down. So the first quadrant, all values of x and y are positive.
Okay.
In quadrant number 2, the x values are negative and the y values are positive.
So
Go ahead.
in one they would be, oh, okay. I see how I did that. I got it backwards.
Yeah. Okay. If we go down to quadrant 3, we've dropped below the x-axis, so the y values are negative. The x values are still negative, so both values are negative. Okay. And when we get over here to quadrant 4, the x values now again are positive, but the y values are negative. Every point in these quadrants can be described by a value of x and y. If we look over here at the second, we're going to assume that each of these little squares is worth 1 point. The intermediate areas are fractional points. So we can go, this point right here is x equals positive 1. This one is x equals positive 2. Midway between them would be x equals positive 1.5. Okay, so we can describe we can put those. Same on the y-axis. So this point right here, 3 points over to the right on the x-axis and 3 points up on the y, would be x equal 3, y equal 3. The point above it would be, go ahead.
Sorry, because of the units, because of the squares?
Yeah, because
That's what would make it, okay.
Because of the squares.
Okay.
If we go up one more, this is x equal 3, y equal 4.
Okay.
We can describe any point by putting in parenthesis the X value and a comma and the Y value. And it's always X value first, Y value second to eliminate confusion. Because if it were the other way, if we had this point here, X equal 3, Y equal 4, we would call that parenthesis 3 comma 4 close parenthesis. Okay, I'll get to that in another document in a minute.
Okay.
If we did it the reverse way, it was 4, 3, then that would be this point. So we have to be very careful that we put the X value first. And it doesn't matter if it's positive or negative. So over on this side, this point right here is X equal minus 4, Y equal 2. So this point would be called parenthesis minus 4 comma 2 close parenthesis. So again, always the X first, the Y second, because that tells you where in this graph you'll find that point. So if you had a point that was minus 2, minus 5, you'd count over 2 to the left of the Y-axis for the X value and down 5 for the Y value. That would place it right here.
Okay. That's
Okay.
simple.
Right. Right. So we use this terminology a lot. So we will be seeing that when we get into constructing graphs later on. But this is the basis for it. Now I'm going to pull up a different screen here. All right, so this basically says the same thing, but it gives you some more examples. Again, this is the origin, 0, 0. So this point over here is 2 over and 1 up, so it's 2 comma 1. This point here is 1 over 2 up, and it's 1 comma 2. So you can see the confusion that would come if we listed these in the wrong order. Another example, minus 3, 2, counting over minus 3 and up 2, minus 1, minus 3, and 3, minus 3. So that also the sign distribution in the coordinates tells you what quadrant they're in. If they're both positive, they have to be quadrant 1. If X is negative and Y is positive, it's 2. If they're both negative, it's quadrant 3. And if the X is positive and the Y negative, it's quadrant 4. So if you remember that, you can always plot a random point correctly. Now, in algebra, we use the entire 4 quadrants. For the most part in business, you generally use just quadrant 1 because what you hope is that everything's positive. If it's negative, if you have some negative values, say you've got a sales trend that is dropping, obviously it's going to be higher on the left than and lower on the right. You could have not negative sales, we hope. That actually comes from returns. My daughter is an author, and she actually got a royalty statement recently where the proportion of her advance that had been paid out actually dropped from one quarterly period to the next because of returns of the books to the publisher. So you can have negative returns. You can also have losses. If you're doing profit and loss, you can have losses. Those would go below the line. In that case, you would have these 2 quadrants. But hopefully you don't have negative sales. So for the most part in business, we don't see the left side of these coordinates. but the principles of using them apply whether you're using one quadrant, two, or all four. Okay? So we call these points where the value of x and y are in parentheses, we call this an ordered pair. And we call it an ordered pair because it's always x and then y. So the order counts. It also, this ordered pair is also called the coordinates for the point. So the coordinates here tell us that 2, 1 is x value is 2 and y value is 1. Is this making sense to everyone? Please stop me if I'm confusing you at all. So we know about the origin. So what we can do with equations is actually take an equation and we'll see some graphs here. So let's take a look at an equation. This one, the format's wrong. This should be x minus 1 squared. I'll fix that right now, in fact. Okay. Okay, this should be x minus 1 squared. So we can actually use a graph to solve this equation. This is a quadratic equation because we are squaring this term. And if you remember, the value of this term, when we square what's in the parentheses, is x squared minus 2x plus 1. Okay. So we can have this this equation, and if we just make a table and substitute a value of x, just that we make up. And usually what I suggest is start with x equal 0. Because it's easy. Everything that has an x in it goes, and all you've got is constants left. So we said that this was x squared minus 2x plus 1. If we subtract 4, then this is x squared minus 2x minus 3. So if we set x at 0, then y becomes minus 3. So we go down here and we plot that right on this axis. Okay, we just put it there, put the point at minus 3. Then we substitute other values. So if we substitute 1, we find that x is minus 4 because we had x squared minus 2x minus 3. X squared is 1. Minus 2x is minus 2, and minus 3, if you add those up, it's minus 4. So we plot the value of y, and we keep going. Another thing to do is to give the x a value of 0 and calculate y. So if we give x a 0, then we've got 0 squared minus 2 times 0 minus 3 is y. So we have x 0 because it's on the line and 3 over here. If we substitute in minus 1, we find that at minus 1, y is 0. And 2 more. This shape is typical of a quadratic equation. And it can be either with the nose down or it can be the nose up. This is called a parabola, and it has a very specific shape. In fact, the parabola describes what happens if you are, say, in the military and you fire a, some sort of cannon. this parabola is the arc that the shell follows. So these kinds of equations are used to calculate where you have to point the cannon and what elevation to hit your target, if you can measure the distance. So we have, and where this crosses the x-axis are the solutions of a quadratic equation. Remember, I told you that a quadratic equation has an x squared term. And when you take the square root, it can be positive or negative. So all quadratic equations have two solutions. And we simply read them off the plot here, where the line that we've drawn crosses the x-axis. So this is a way to solve it without going through any other work, is simply to graph it, right?
So we would graph the two different solutions.
Yep. You end up with both. Wherever it crosses this x-axis is the two solutions to y equal to this, to a quadratic equation.
Okay.
All right. So we can take a quadratic equation and do this. If we look at this, remember, a quadratic equation doesn't necessarily be y equals, it can just be the equation. We can still graph that, and it tells us what the values of x are. Okay. So where the line that we draw crosses these axes is called the intercept. That's a mathematical term that just means where it intersects with the axes of the graph. So that's a term. We have an x-intercept, and of course we have a y-intercept. Here the y-intercept is -3, where it crosses that axis. This is not drawn as well as it should be, because this dot here should be right on the 3. Okay, so we use these kinds of ways. So remember, to find all we have to do to find these intersects is to set x equal to 0, and then find a solution where y is 0, a place where this equation equals 0. So you choose a value of x where that can happen. That's why we use a table and just line them up. Okay, is this making sense?
Yeah, I'm just gonna have to try it and do it, and then it'll make a lot more sense.
Okay. So that's, we'll come back to a little bit more about solving equations with graphing later. I want to go to discussing the kinds of graphs that we are dealing with. So let me pull up a okay. I'm going to start with bar graphs. You're quite familiar with these. What they do is present information that we've derived in a, sorry about the noise, they're scraping up tack track in the basement. Can everyone hear me clearly? Good.
I can.
Did someone say you can't?
No, I said I can.
Okay, great. Thanks, Jennifer. With a bar graph, all we do is a very simple statement. And this little graph here is simple. You've gone out and talked to your friends and find out what kinds of movies they like best. And so what we have here is basically the number of responses for each of these favorites. So what we've done then is set up a graph. We have, see, the origin here is the 0 point, the y-axis, and the x-axis. We have chosen in this case to put the type of movie on the x-axis, and the number of people that respond to for each one on the y-axis. We can choose lots of ways to present this information. What we don't want to do is make this so high on the X side that these numbers look exaggerated or so low that they look very small. We want the differences to be clear. In this case, they are pretty well because we've set this up. Each of these lines is one person. So we can see very easily that the largest number of responses, this does not mean the majority, it just merely means the largest number, was for romance movies in this particular survey. So this gives us a very quick glance. We can see this immediately. No one has to explain to you which one has had the greatest number of responses. We can show in other ways as well. Note also that this was done in different colors. Colors are a good way to set off data because it makes things, it gives enough differentiation that you can actually, you don't get lost in wondering what you're looking at, okay? So another one is 145 people have been asked, what is the nicest fruit? So we have a list of 6 different fruits, and your own personal favorite may not appear there, but that's the way it goes. And then the number of people who chose each one as their favorite. So again, we present this in different colors. Obviously, the colors were chosen. Again, you can look at this. My only quibble is that the apple can be a lot of different colors. But it's pretty obvious that even from the colors, which one we're looking at. But we've had to group this in units of 5 in order to keep this from going off the top of the page. So we set up our scale such that that it can be at a size that's useful for whatever format is your presentation. We can do things either vertically or horizontally. There is no right or wrong way to do it. It's dependent on your own personal preference. A lot of people prefer these, I think, because it's easier to see heights than different lengths, and that may be a bias on my part. But again, we can either have a horizontal or a vertical bar graph. Okay. Going back and looking at grades, we have students in a class who got the following distribution of grades. 4 got an A, 12 a B, 10 a C, 2 a D. So we go down here and we can plot these out and make it very clear that the largest number of grades was the B. So the B and C dominate. They take up most of the data. So we can present it in this fashion, putting spaces in between the bars often will help differentiate them. But I want you to note that these are what we call discrete data. I don't know, has anyone taken statistics? You have, Jen.
No, not yet.
Oh, not yet. Okay.
Not yet.
Okay. You'll get into the concept of of discrete and continuous data. In fact, we need to talk about the portfolio assignment for next week. It's about statistics. So we'll need to look at that because I don't have any idea what your assignment actually is. I can't see it
Because
for
it's
each
in
of you.
portfolio.
But we have we have this discrete data. There is no continuum here from apples to oranges to bananas to kiwis, etc. Where and there is you either get an A, a B, a C, or a D, even if you differentiate them as A minus and B plus and that sort of thing. There are distinct values that we can place on them, whereas some data, such as height or looking at blood pressure in a group of people. These are what we call continuous data because they can have any value along a line, a continuum of values. And in that case, when we have that, we take out the gaps. If we look at this particular one, we won't talk about, we'll get to what these data are at another time perhaps, but we have, this had to do with looking at expenses for in a couple of different countries on expenses on certain items. Where we have continuous, it's very hard to plot something where you have every single possible value. Saw a plot of birth weights of babies. And birth weights of babies, generally speaking, they're going to be in a fairly narrow range, but they can be any value within that range. So what we do is give ranges for these things, and then we make we make the bars right next to each other. We put no gaps. This is called a histogram. So the difference between a bar graph and a histogram is that bar graphs are generally discrete data. There's no continuum between US, India, UK, New Zealand, and Japan. Discrete data versus data that could be continuous in nature. This is important because then we're not looking at huge numbers of bars on this gap, and we really don't much care about much of it. So if we were looking at at say at blood pressure, say the diastolic or the systolic blood pressure, the top number in your blood pressure measurement, we might work that as a range of say 5 points or 10 points, because the difference between a blood pressure of 109 and 110 is irrelevant. So we give a range, and then we make that, because that's a range, we use these range numbers. We set them up to where the boundaries, the lower and upper boundaries of each range are these points between the bars. So that's the difference between a histogram and a bar graph. And we're going to, questions?
So in business, would we be using histograms a lot?
It depends on what you're presenting. If you're talking about, say, weekly sales, yeah, you'd use a histogram because your sales would have ranges. You wouldn't have specific dollar amounts. I mean, your measurements would be there, but when you presented the data, you'd be looking at those ranges, right? Or you might look at, the effect of sales of discounting on pricing. You might do ranges on that as well.
Okay.
Discounting on sales. So there are plenty of places where you would do that.
Okay.
Let's go ahead and take a break. I'll put the recording on pause. Okay, is everyone back? Ready to get started?
Yep, I'm ready.
Yes, sorry. I was just doing some homework.
No problem. All right. So now we're actually going to look some more at histograms. Remember what I stated earlier was that it's like a bar chart, but we group them into ranges, which is why there are no gaps between them. And so basically, the chart shows by height how many of whatever it is you're measuring fall into each range. So if we look at the height of orange trees, they vary from 100 centimeters to 340 centimeters in height. So if you decide to put those results into groups of 50, how do we choose what the groups are going to be? That are what the ranges are going to be. We look at the data and see what makes sense. What we don't need to have is a couple of dozen of these bars. That becomes harder to visualize and interpret. So we want to make things sensible and look at those ranges. We generally we like to have between no more than 5 or 10 ranges. Any less than 5, the ranges are too great. Any more than 10, and the ranges are too small. And again, it depends on your purpose. With something like this, putting them into 50 centimeter ranges makes a lot of sense. Okay, so that so this means that we leave a gap at the beginning to show that this is not the 0 point on the far left. When we don't go down to 0, we need to note that to make it clear that our data range is no less than that. And the same at the top, we leave a little gap there to show that we've terminated this and we don't have any data any higher. So we display this. They've chosen to have 5 ranges, which makes sense when we're looking at these number of trees. We've got 50 here, and we again, the number this scale depends again on the data. What you want is to take up a good portion of the graph, but you want to leave some blank space at the top to show for sure that the data stop at this point of 50 in this case. So the presentation here makes it clear that we don't have any range that is above, that has more than 50 data points in it, and that we don't have anything less than 100 centimeters or greater than 350 centimeters in height. So that we can look at this, and again, these ranges are sufficient that it's fairly easy to see differences. Here it looks like this could be 27, okay? So I don't see a table of the data, so that's okay. It's not really relevant. We see that the vast majority of the trees are in this range. We have a few that go on either side. Again, these are continuous. These links here work. They can take you to a site on mathisfun.com, which I know some of you have already been on, that can help you with constructing these if you want to. And you'll see these in several of these, see these kinds of links in several of the things that I give you today. So the horizontal axis, the x-axis here is continuous because the data are continuous. This means that we can have a tree that is as short as 100, but it has to be less than 150. So it can be as short as 100 to as much as 149 centimeters. This starts at 150 and goes to 199, or if you want to really be tight on it, 199.9, but I don't think anybody measures tree heights to a millimeter. But nonetheless, these are the beginning. These numbers down here are the beginning of the range of each range, which means that the range ends just before the beginning of the next one. So we would not double count a tree that was 200 by placing it in both the 150 to 200 and the 200 to 250 range, right? So that's another characteristic, okay? Looking at growth rates. In this case, we're looking at a cute little puppy. And so you've looked at weight for the puppy and how much they've gained. This is just a difference. It's not the weight. It is the difference in weight in a month. So we've got half, I'm going to call these pounds. So we'll call this half a pound, 3/10 of a pound, lost 2/10 of a pound, gained nothing, and some small numbers. So we are going to vary from minus 0.2 to 1.6 pounds in a month. So we put them in order. That's the next thing you do. Arrange the data in order, lowest to highest. And then decide to put your results into some kind of range. In this case, the choice is to make it a half a pound because we have a couple of dogs, that's a reasonable difference between minus 2/10 and 1.6. So now we create 5 ranges. We set up our ranges first, minus 0.5, meaning the puppy could lose weight in a month. And that's, reasonable. But again, we put this gap here to show that the range starts. You'll note that this 0 is over here. And that is really to show that, that we're using an X and Y axis and the months of 0. So our range here, we actually do have a 0 point in a range, minus 0.5 to 0, and so forth. So we do this, and then we simply count up the numbers that fall into each range. We have 1 month where the puppy lost weight. We have, and so we have 1 month here where there was no weight gain. Okay, so in that particular case, we've got 0, and then 0.1, 0.1, 0.3, 0.4, and that's where we stop. There are 5 of them, 1, 2, 3, 4, 5. Note the 0.5 is the beginning of the next range. And we take that up, we have 3 at that. There is nothing between 1 and 1.5. So we leave a bar at 0. That's a 0 bar. Okay, and it's connected to these because the value here is 0, so it's right on the line. Some people will actually draw a heavy line across the 0 to emphasize that there was nothing, that there were none. And so you have 1 value in this other range. So again, we can see that, the rate of gain was, the most common again is in the no gain to just under half a pound. So we do that. The range is called a class interval. Each class this is the class of of a half a pound, of negative a half a pound, positive between half a pound and 1, etc. That class interval is there. So again, if we look at categories, and we'll look at this is this is just a presentation of some data. A frequency histogram is something to show things like scores on tests. You know, as the scores can range, and we use these things also for, you've seen all these surveys that say rate on a scale of 1 to 5. And so again, we take the data and use these frequency histograms. The range here is 1 because we only have 5 possible values. And so what we see is that in this particular survey of maybe a satisfaction, the largest number was 2. We hope that 1 is very good and 5 is bad, but you know, we don't know. So all we do is then list what these are. And again, we can see this very, very clearly. We use histograms here because the scores are natural ranges. You can't give an answer of 1.5, for instance, to a survey like this, even though sometimes I want to. But you can't do that. And these are common. You'll learn in statistics why these are also often worthless, but that's okay. But you'll see these very commonly. We see them in virtually every survey and that you might run into. The temptation is to give it some sort of rating. And so these are something that you would possibly be presenting. Okay. So questions? Okay. So let's look at pie charts. You've all seen pie charts.
Mm-hmm.
What they do is, again, in a very visual way, show relative sizes of data. So again, let's go back to that movie survey that we had two pages back here. We can see these. And the use of a pie chart always involves listing percentages as well as numbers of the values. The values often are left out if those numbers of responses or the number of occurrence is very high. If you're looking at population data, say in a survey, in a census. So again, this is very quick. You can see the very biggest section of pie is romance. That's obviously the largest section. We start at some point and going usually counterclockwise, we go from biggest data set to smallest. So here we've got 6, 5, 4. These two are the same, so it's irrelevant what order they go in. And then lastly, the drama section. So it's a real quick way. Now, this works well for small numbers of categories. I have seen pie charts with 50 different categories, some of which are like 1%. And there is no way that you can interpret something like that. So this brings up the need for looking at exactly how we're going to present our data. if we have too many categories, we need to find a way either to reduce those categories, usually by using some form of histogram presentation, or redefine how we're going to present it. Pie charts with more than about 10 or so different segments become very difficult to interpret. So as I say, I've seen them with as many as 50. You look at it and you say, you know, you throw it out. It is meaningless. It is poor presentation. Again, this is something that we look at. What you want is for, you know, it follows. You remember the KISS principle: keep it simple, stupid. You know, it was really something that became popular in the Bill Clinton days, but we've known it for years. We need to keep things easy for people to see. Executives especially are notoriously impatient with things they can't readily grasp. So if you have a point to make in a presentation, you know, that's why we keep it simple. We keep the presentation simple, not simplistic. Don't insult your colleagues by making things simplistic, but keep it understandable and keep it something that can be interpreted. Okay. So there's lots of ways to make them. We can think about these things. And one of them is to look at, we can do this the hard way. We can calculate our percentages, and remembering that a full circle has 360 degrees, we can use that as a way to calculate percentages. 20% of a data set would be 0.2 times 360, 72 degrees. So you can measure this using a protractor, or forget that and just use the charting, the graphing functions in Excel or Word. And again, you structure this to come up with something that they will calculate for you. Laboriously, back before we had the computers and stuff to do all this for us, I can remember laboriously measuring all these things out to make presentations. It was a pain in the neck. So nowadays we have some very nice tools to make things much easier to use. So you can show lots of different kinds of data. Let's take a look at student grades. Again, we go back to the same one we had before in a previous when we did a bar graph. A, B, C, and D. So here is a pie chart that takes that data. This, by the way, assumes that there are only the 4 different grades, that none of the students failed, okay, on this test. So we're assuming that this, because it assumes that this, when you're structuring a pie chart, it assumes that the data that you have is 100% of the data. So again, it's really obvious the biggest chunk of this is the B. They have done this in my training for preparing these. They've done this wrong. It should have been, the B's should have been here. The C's should have been the next one around, and then the A's and the D's. But what they did was they started with A, B, C, and D and made that clockwise. There's, again, standardly you go from largest to smallest, but if you have a different reason or a reason to present it differently, you do it. But most people are used to seeing these things being largest, next largest, etc. This does not work either in clockwise or counterclockwise directions. So, but these are ways we can present this, and it's easy enough to do. One of the reasons we don't want too many categories is then we have way too many colors. And once you get past the basic, red, yellow, blue, green, etc., then you start getting into slightly different shades. And so that too is confusing. So always, if you're preparing these, especially for a presentation in business, look at them. Ask yourself if this actually works, because it may or may not work well. Hang on. Just got an email from Cody. Is anyone having trouble with their technical issues with the students? With your computer, rather?
No.
No, mine's doing pretty good.
Okay, good. Because Cody's asking. He can't walk into the room very easily. Okay.
Unless he has the code.
Okay, so any question about pie charts?
No.
All right. Let's look at line graphs next.
I know the stuff that I want to do, graphs are definitely useful, helpful technique for, especially when you're doing like something that you need to see more visually. A graph is definitely hits that spot.
Yes, it does. If you think about, turn to any math book, and in the back of the books, often there are tables, and especially in the textbooks that we've used in the past, there are tables of data, and you look at this, and it's just page after page of columns of numbers.
Yeah.
And I look at those, and I've had to deal with those things in the past, and you can really get lost in those, and they have no meaning, especially if they're not in any sort of order. If you're looking at a table of numbers that is in order, either lowest to highest or highest to lowest, then you can often find that a little easier to deal with. But if it's just looking random, or if it's whole bunches of decimal numbers, then most people really want look at that and say, okay, that's very interesting. What do I do with this?
Right.
And so that's why we use a lot of graphical analysis. We do see huge data sets. Right now we're involved in the decennial census in the United States. You're going to have a data set of, 100 million households or more. There's no way you could look at that data set and make the slightest bit of sense of it without computing power to do the work. So it depends on the size. Fortunately, most businesses are not going to have millions of data points in their presentations. So a line graph is something that you're going to see. We see these a lot. In fact, there is a line graph that I put into my discussion post that you'll see when you read my post. But if we look, a line graph is merely information. Okay. A line graph is merely another way of presenting information, showing generally to connect that information to show changes, like changes over time, or increases in sales, or increases in profit, or we hope never decreases in either of those. But we do present these things, and it makes it possible. What you're seeing here in this very simple thing, facts that someone is learning about their dog, maybe. So these learn a few, and then a lot, and then some more. And you can see that over time, you're accumulating more information. When you did, this is a rather simplistic example, but if you were looking at this, you'd say, yeah, I'm learning. But we use these things a lot, and more appropriately, we've got a line graph. We're going to look at the relationship with ice cream sales to day of the week. And if you look at this little table of weeks and of sales, you see something you might expect. On the weekend, you're going to sell more than during the weekday. Okay, so here's an example of how to make this graph. We draw a vertical scale and a horizontal scale and give it labels, and we make our little tick marks. We've established sales values. I don't know how well you can see this, but this is 0, 200, 400, 600, 800. Note that the top sales was 790. So the top of that vertical scale is above the highest data point. Okay.
So you got them by 200, 400, 600?
Yeah, 2, 4, 6, and 8. Okay.
Is that just to keep it organized?
It's to keep it organized, and so you can actually, and obviously going up because you want to see what your sales are on this, and hopefully your sales are going to be up in that range. And then our x-axis is just the days of the week. Note that these are not numbers; these are just things.
And Y goes down, X goes across, right?
Pardon?
Y, X. Y,
Yeah,
X.
Y is vertical, X is horizontal. Okay, so we label those, and then we place a dot for each sales number. So we had on Monday, if you look at this, 410, Tuesday 440, Wednesday 550, Thursday 420. So we put a dot for each of those numbers and then just connect them with straight lines. Okay, because there's no reason for these lines to be curved, for the simple reason that on, we have discrete values that we've measured on Monday, Tuesday, etc. So we can see that our ice cream sales go up. The difference between Saturday and Sunday is rather small. So we're not terribly worried about that. Why does Thursday go down? Who knows? This is useful as a 1-week data set. And what you may want to do over time is accumulate this data and maybe calculate the average sales on Monday, etc., and see where those go, see where your best days are. Is Thursday always a bad day relative to the others? And really, it's not bad. It didn't drop below Monday. So, but is Thursday always going to be lower than the preceding and succeeding days? So you may want to, look at this. So this is common. We see this in sales, like monthly sales figures a lot. We see placing numbers and looking at what's going on. And especially retail will use this as a way to look at monthly sales depending on what it is you're selling. If you're selling clothing, there are going to be times of the year when you'll sell more and times when you'll sell less. If you're selling camping gear, this is something that all the big box stores whether it be, you know, a giant box store like Costco or Home Depot or a local hardware store. They're going to be plotting what it is they sell when, and use that as a way of determining how they're going to inventory things. It gets a little ridiculous. A number of years ago, my wife was a home health physical therapist for 40 years, and she used to help customers or help her clients sometimes by um, uh, uh, getting small equipment. There was one time when a client needed a vibrator to massage tense muscles. And so she went to Walmart and they said, well, we don't have any vibrators because they're seasonal. Now,
Wow.
you know, that made no sense. But that is something stores do. They determine when they're going to sell things, and that determines when they're going to stock them.
Because they go by the number of sales they had the annual year, right? The last
Yep.
annual year. Yeah, that
Yep.
makes a lot of sense.
Yeah. If you go, for instance, to Costco, we shop at Costco quite a bit. Well, we used to. These days, it's once in a while. But you go to Costco, and in February and March, early March, they have corned beef by the ton on the shelf because of St. Patrick's Day in March.
That makes
Day
sense.
after St. Patrick's Day, they put the rest on sale, and you don't see it there for the rest of the year.
That's smart business tactics.
Yeah.
I'm catching on to these little things.
Yeah. And you go to a garden store, you know, they'll have your spring flowers on sale, but you can't get a spring flower in September because who's going to plant a spring flower when they're just going to get frozen, right?
Right.
So they really do take a look at these, and these kinds of line graphs are good for helping with that determination. But taking a point, a single time period, like one random week, and you just do this only tells you what happened in that week. What you need to be doing is looking at these things over a course of weeks. Ice cream sales, of course, are going to be very low in the winter, not zero. It's amazing how often people will eat ice cream when they're standing in the snow.
For some reason, I used to eat Sonic and everybody gets shakes when it's a snowstorm. And I'm like, how are you eating ice cream? Go eat the snow.
Right.
That's gross, but
clearly, when the weather starts warming up, we'd see these sales go up. We have a friend who has an ice cream truck business. So this is something that he does all the time and looks very carefully at when he's selling the most of various different things and stocks his trucks in that way. So this is something that we do all the time. This is going to be, in terms of business, a very important way to look at data. Because again, you can look at this data right here, and in a week you can say, oh yeah, we sell the most on weekends. Well, that's pretty intuitive. Many years ago, when I was a college student, I spent a summer driving a Good Humor truck in outside of Washington, D.C. And believe me, in the summertime in Washington, D.C., it's hot as blazes. And I sold a lot of ice cream on the weekends. I'd sell twice as much as, say, I'd sell in a Wednesday or a Thursday. And especially on the weekends, the kids were back from summer camp. So a lot of the kids were buying. In the middle of the week, a lot of them were gone. So it was a case of knowing that that on the weekend, I better have my truck stacked to the ceiling. So it was really kind of, it was an interesting experience. I can tell you some hilarious stories of that, but I won't waste your time on that today. Let's look at a couple of other things here and look at dot plots. dot plots are a variation really on bar graphs. Okay. If we look at this, a dot plot is, again, it's essentially a graphic display of every data point that we have. Okay. How long does it, okay, let's look at this survey. How long does it take you to eat breakfast? So we take our answers. The answers are our range. Okay. 6 people said they don't eat breakfast. So that means that it takes about 0 time to eat breakfast. But we've got, at the other end, we've got 7 people who spend 10 minutes on breakfast. These are all obviously estimates. So, so we have other people here, other data points. So we have, and the answer is in minutes. So these are our data. So our x-axis here is simply the number of minutes. We just list them out at a time. We can use ranges. I've seen this done with looking at the presentation of blood pressure data. We can have ranges and numbers of people in those ranges. But the issue here is we don't need a y-axis because we're going to put a dot over every number of minutes, 1 dot going vertically for each person who answered at that level.
Oh, okay, that's pretty simple.
Okay, so this is every single data point. So we've got the data points are the number of people who have given us answers. So we've got 11, 16, 18, 23, 25, 28, 35. We've got 40 data points here. So we have 40 dots on this plot. So we can easily see this. And this is the best use for a dot plot is when you have a reasonably good sized set of data points, say under anywhere between 20 and 100, that you can present in this fashion. And it's easy to see this. Now, it's easy to count 2 and 3 and 5. Most of us can do that visually, but sometimes we have to count these up. But nonetheless, it's easy to see that we've got a bunch of people that don't bother with breakfast, but that the largest number of people spend 10 minutes on their breakfast. So again, and we see that there is no one in this range. And very clearly, we didn't get any, we got no responses in this range. So when we did this, when we're looking at minutes, notice we went every single minute up to 12. Even though 2 of those had no data, we want this to show that there were some gaps in the data. Okay. Now, another way you can do it is put a vertical scale and then just put a dot at the highest. This is not the most common way because, again, you can read a lot of this visually in this top of this dot plot. But down here in this bottom one, we have to look over and say, okay, where is this dot? Oh, it's at 2. And where is this dot? Oh, it's at 3. So we have to look across and see this. So we have, and this dot, note that the squares are there. It's hard to read this scale, but there are little bitty faint lines between the darkened squares, so that we actually have a line here. So anyway, this is another way to do it. Now, this is a mistake. We've got 2 data points. Do we have 3 or do we have 4? If the idea is you just put the 1 dot for the highest value, so this one is incorrectly done. You would look at this and say, why is that there? Is it out of place? Is it supposed to be someplace else? So when if this is done correctly, that dot would not be a part of the plot. Okay. So another way of looking at this is by what we call grouping. And again, grouping is the same as the ranges in a histogram. We have a range. So we're looking at a whole list of countries with percent of the population having access to electricity. There are 212 countries on the planet. So we theoretically could have 212 numbers. But what we want to do is, again, we can't have 212 data points on a readable dot plot or histogram or bar chart. That's just impossible. So what we do is we want to put we want to reduce the number of data points by putting in ranges. And we don't, and our vertical scale here can be anywhere up to 100 with lots of data points in between whole numbers. So we put them into groups, and we look at access again as a percent of the population to the nearest 10%. So we see Algeria was listed at 99.4. We got 100. That averages out. Angola, 37.8. The nearest 10% is 40, etc. Okay. So we have a huge group of countries. So then we can group them in a different way. We can say the number of countries with where 10% of the population has access to electricity, 20, etc. Now we have 10 different basically ranges, categories of these, and we can take a look at this dot plot, and it shows the data, but it's pretty cumbersome to count this, right? We know from our data table that this is 34 dots, but if you're looking at this, what you're saying is how many is that? So this might be better to put with a scale on it that shows gives a better example, because you'd have to count these. If you didn't see this table, you'd have to be counting all of these. But it's very clear that a plurality, the largest single grouping of countries, we have essentially 100% access to electricity. Okay, does that make sense? These are useful. They have a visual impact. We have, a small proportion of all these countries where 10%, 5 countries where only 10% of the people have access. Does this make sense?
Yep.
Okay. Let's do one more. And we'll take a look at something called a scatter plot.
Scatter. Is that also a graph?
Yes, it is. A scatter plot is a way of looking at the relationship between two sets of data. One of my favorite examples, I don't have it on here, but I will tell you, is a number of years ago, as part of a statistics class, some people decided to see if there was a relationship between the price of a slice of pizza in New York City and subway fare. And so they went out at various times, and they would go and do a quick survey. What's the price of a slice of pizza? Take the average. And they would look at subway fares as well. And so they plotted them out. those are, we call this an exercise in looking at the relationship between two sets of data. Now, clearly, and what they showed actually was something that looks a lot like this. It looked like, except that this was price of pizza, and this was the subway fare, and they went up together, and it sort of looked like they were related. Now, clearly, the price of pizza doesn't affect the subway fare, and vice versa. So this is something that shows a relationship that obviously is not causative. It just is something that happens
Very different.
at the same time. And it, to finish that story out, if you added in inflation and compared the inflation rate with each of those, then obviously it was related to inflation rather than each other. But it's a way of looking to see if there is something about two sets of data that is changing the same way. So again, if we look at height and weight, obviously we would expect that you know, height and weight were indeed related. And if we looked at a whole bunch of people and took those data, we've got height on this axis, could be this one, doesn't matter, but height and weight. And we simply take that person's height and weight, and so the weight becomes your X coordinate, and the height becomes the Y. So this is, and note we don't have any numbers on the scale, so we don't know what they are, but it's not relevant to this. So this is used as we just plot those two data points. So in the case of the pizza, this might be the price of a slice of pizza and the subway fare on, you know, say the first week of March. And then we might look at the first week of April and find that there was a slight difference. But it doesn't matter. Here we've got a weight of some amount and a height of some amount. So we simply plot that as an XY ordered pair. So let's take a look, go back to the ice cream sales. And now let's rate ice cream sales versus temperature. And so we've got 12 days worth of data here. And the temperature here is in degrees centigrade. So for instance, you know, 25 degrees centigrade is 77 degrees Fahrenheit. Okay. So if we look at this and plot that data, we've got the temperature in degrees centigrade and sales of ice cream. And we can see that as it gets hotter, we get more sales. What we have here is raw data. What we have done here is put that data into a table that goes, that relates temperature increase first, and then the sales for each temperature. Here it's pretty random. 14.2, 16.4, 11.9, etc. So what we've done, we can either arrange the table in ascending order of sales or ascending order of temperature. But either way, we plot this. So on this day, the temperature was just under 12 degrees centigrade and sales were just under $200. So we plot these out. So we put them at approximately where they are. We can look at this and see, oh, okay. So we have an obvious correlation here. When it gets warmer, people eat more ice cream. Well, duh, right? We can then use this as and put together a line, estimate a line that goes through most of the data points. We can either do this by eye, which is fairly easy in a narrow data set like this, or we can use some calculations for that. we can have much more data. Okay, so we're looking here at sea level rise. So there's a dot here for various times in these 2-year intervals of measured of sea level data over time. Some of this is seasonal. Some of this is not seasonal, but it's fairly well done. We can see that we could put a line through here. We can run it through a complicated analysis and come up with a straight line. So here we can put this line on here, and what that says to us is that, and we're looking at changes basically in sea level in millimeters. Millimeter is about a 25th of an inch. So what we're seeing is changes over time versus a point that we have chosen as our 0 point. In this case, approximately the year 1999. Gone back and looked at data and looked at both sides, so that this line here tells us what that is. So if we can use this for predictions. And we have the process, what we call interpolation, which is finding an unknown sales. Now let's go back to the ice cream, finding an unknown level of sales we might expect at a temperature that wasn't actually measured. In this case, we have no data between approximately 19.5 degrees centigrade and 22 degrees centigrade. So we could estimate that our sales at 21 would be about $480. Being careful to understand that they might be a little bit higher or a little bit lower, but this is what we could think about as our sales at a day when the temperature was going to be 21 C. Extrapolation is when we go outside the data set. Now, this is risky. And the reason it's risky is that we are assuming that there are no other factors that are going to make this line maybe go higher or maybe lower. So here we're looking at, what if the temperature is 29 degrees centigrade? Then we're estimating our sales at this level, but it is risky. And it is because we don't have any data beyond this. Okay. So, okay. We'll get into that later. We'll get into linear equations in a little bit. We can have negative correlations. Here we have a positive correlation, highly positive. When the data are too scattered out, but it looks like they're generally going up, we call that a low correlation. When the data are just all over the map randomly, there's no correlation. So it can go the other way as well. Just because, we've looked at things that go up relative to each other at the same time, doesn't mean that that's always going to be the same, right? We might look at sales of bathing suits, which would start going up in the spring, but they'd start going down in the fall at the end of swimming season. There still might be some sales for people that head off down to where it's warmer and go to the beach during the winter, but not as much, okay? So we can have a low negative, a high negative, and a very nearly perfect negative correlation where everything falls directly on the line, okay? So an example here might be birth rate and income. we find that the data are very clear that in higher income countries, the birth rate is lower than in lower income countries. So this is not exactly, this straight line that's been drawn through here. Note that we start getting a great deal of spread the lower the income is. And when we get down very low, we start going way up. So that tells us that this correlation works best from about here to here. But when we get lower, there's a different correlation. Okay. Everybody, does that make sense to everyone? Okay. It is now time. Let's take another break and come back later. And I think we'll do a couple of other things. And then in the last little time, I'll talk some about linear and quadratic equations. Okay. So let's take a break. Okay, I've resumed the recording. What I thought was now's a good time for me to be quiet and have you guys go back to looking at the discussions, assignments, etc. For this week and get started on that. And if you have questions, you can ask.
I do have a question because I was reading it. So we're discussing one or two of the unexpected graphs that are helpful in our business and our future. Is that correct?
That's correct.
And then it also says, sorry, my computer is being weird. It says, describe how you feel graphs would be helpful in your career. What
Right.
types of information would be easier if viewed in a graph? So basically, like if I wanted to be a financial advisor for like a supermarket business, we would definitely be looking at revenue and salaries and stuff like that. So basically are we showing a graph? Or are we just explaining?
Well, if you want to show a graph, that's fine, but it's actually just asking for an explanation.
Okay.
Okay.
All right. So we're
Describe how you feel it'd be helpful in your career and what kinds of information. If you can find a picture of a graph to present, you can embed that in the response in the post.
And you're still okay with YouTube citations?
Yeah. Or actually, I think it just is one citation is all that's required. Two will be fine. You can put as many as you want. I know in some of my posts, I've used up to 5.
Yeah, I've used a lot too, because I take information from different things.
Yeah.
Helps me learn.
Well,
Okay.
it's useful to learn to credit the sources that you get your information from.
Right.
Even if it's just some minimal part. I mean, if you look at a lot of reports, those that are really trying to follow the guidelines for citing other people's work, they'll have many citations, even though they might only have a sentence or so that's taken from one. That's okay.
Right. If I use any information from anything, I usually cite it.
Good. That's the safest thing. Nobody's going to fault you for too many references. But you do need to put in your text, you need to put some citation for the ones that you're using, because otherwise you can just throw a bunch of citations down and not actually use any of them. Unless you let us know where in your writing you are using that information. Okay.
So do we need to type that reference in as well? What you're saying is safer?
The in-text citation is the author's name and the date.
Okay. So
Okay,
those are the
that's all
most
you need.
important.
Yeah, and that can be anonymous, and it can be an undated thing that you've gotten off the internet. Okay, but you still need to put that in. And if you have the same author, like anonymous, and the same year, label one A and the other B.
So they know it's different.
Yep.
Okay.
Yep.
Gotcha.
And off websites, that's common because many of them are anonymous. Even though they're very different subjects, they may be, there will be no named author, so it's anonymous, and they might not, they'll have a date. If you're lucky, you'll have a date. Sometimes you don't even have that. So that's why we use the ND for no date or not dated.
Okay.
So if you have multiple of that, then label them A, B, C, etc. And then just put it in a parenthesis at the end of wherever you've cited, wherever you've used the information. Let's take a look here. We should have that up here. They've got a bunch of, they're not including those here. Naughty, naughty. Let's just go down to, where is that? You mean I have not included that? Something's wrong here. I don't think so. What happened?
It's starting to rain here.
I think it's raining here too.
On it.
It's
Nate,
cold
can I do
outside.
graphic arts?
Graphic art.
Do you like it?
Yeah, I do.
That's what I was gonna do at first, and then because I wanted to have an art studio, but I decided, I want to own a business, so maybe business is probably where I need to go first. So that's cool. I'm an artist. That's pretty tight.
That's good.
Do you have stuff? Do you have stuff on your Facebook?
Yeah,
Oh, awesome! I'll check it out.
I'll send you my link.
What's that?
I just send you my link.
Okay, sweet. Thank you. I think I added you.
Does anybody know how to get to like how much you've already paid for your tuition?
So,
I mean, I know the payments for like getting to the payments, but I don't know how to get to the ones that to show how much I've already paid and how much is due. Probably have to talk to Brianne about that.
what I was gonna say is maybe Bree's the best question answer for that.
Because I got a loan or not a loan, a grant for this COVID stuff, and I've paid about 500 from it. So
You're just trying to get your receipt, or I would talk to Bree on what you owe. She could tell you everything.
yeah, I'm just trying to see how much I owe for everything for the tuition.
Yeah, I understand that. You're doing what I'm doing, the whole budget thing. Fun days.
Oh yeah, and it's like $10 a month for me because how much I make. But
Right. And your mom. It all plays a role.
oh, my mom doesn't work, so
No, you're a mom.
yeah, being a
You're a
mom.
single mom. So it plays a role in there in the deductions. You'd have to talk to Bree about that, babe. I don't know.
I also have a deduction for being a person who is a daughter of the person who went to school before me.
Oh, okay.
Canada.
They
They
have
have
some
a discount.
deductions. I
Yeah.
got it.
So yeah, that's fun. Just kind of like, how much do I owe? Because my mom still owes a lot on her tuition, but I'm not my mom, so
Right.
love my mama. I'm not helping her get out of debt.
Oh man, my mom said something to me the other day. She was like, I don't know what I'm gonna do if I ever lose Eddie, because that's her ex-husband. I was like, I'm never gonna let you lose your stuff. So that's why it's important. Get your degree.
Yep. That is what I'm planning. Is to get my degree and then pay off everything once they actually get a really good job, and then I'll be good to go.
My internet is so unstable right now.
Is your internet box cluttered, or like is near clutter or something like that?
I don't know how to even check that. How do you check that?
So if you have